Hivani. I'm first time in India and I happy be there. I enjoy from this country, enjoy for this hospital, very friendly and opening hospitals. And I would like to thank you, a lot of thank you for organizers and also for all participants, because today is Sunday, time to rest, but for original scientists, speaking and communication with colleges, know about something interesting is also part of rest. So enjoy from our section. I would like to request for the first presentation in our section is Maya Krishnan Gopiraman from Shunshu University, Japan. Welcome.
Thank you, Professor, for the very kind opportunity. And also I would like to thank to Professor Behra for his invitation. And today the title of my talk is Electrospun Nanofibers as Multifunctional Platform for Catalysis, Energy and Environmental Applications. In this talk I will share some of the recent research progress of my research institution, Since University, that focusing on development of nanofibers for its potential applications. I hope this presentation will give you some basic idea on what is electrospinning and electrospun nanofibers. So this is the outline of my today's talk. I will give brief introduction on Since University. Then I will move to electrospinning, what it is, and how the process works, and what are the techniques to produce the nanofiber. And then I will move to its potential applications in energy, catalysis, environmental and biomedical applications. I will touch very briefly. Then I will brief the scope of the nanofiber. What are the future scope for the electrospin nanofibers. Then I will show some commercially developed products from our laboratory. So this is the outline of my presentation today. So to begin, let me briefly introduce where our university is located. Japan has 4 main islands: Hokkaido, Honshu, Shikoku and Kyushu. Since University is located in Nagano Prefecture, right in the center of Honshu. It takes only about 90 minutes from Tokyo by bullet train. So it is very easily accessible. Nagano is famous for its mountain. Out of 21 mountains in Japan that are over 3,000, that are over 3,000 meters, almost half of the mountains are in Nagano Prefecture. Almost the region is known for its hot spring, so the people often call it as a hot spring paradise. Actually, this place became very famous after hosting 1998 Winter Olympics. So if you have a chance to visit Japan, please don't miss this place. So our university has 5 campuses with 8 faculties across 4 different cities. The main campus is Nagano. Nagano campus focuses on art, economics, science and medicine. Matsumoto campus is mainly focused on education and engineering. And Minamo, dedicated for agriculture. And Voida campus is our campus, is mainly for textile science and technology. Here you can see the panoramic view of our Faculty of Textile Science and Technology. It is not very large campus, but it is very specialized and extremely active in research. Our faculty has very long and unique history. It started as an imperial university in 1910 with primary focus on silk. Later in 1944, we expanded into polymeric chemistry, chemical fiber, spinning, dyeing and many other textile related fields. Over time, the institute evolved, and in 1949, it received its current name, Faculty of Textile Science and Technology. Today we have 115 years of history. And something interesting is Japan has nearly 800 universities and about 2,600 faculties, but ours is the only textile focused university in the country. So it is quite special and unique. We currently have 4 departments and 6 research institutes. All these departments revolve around one central theme, fiber. Textile science is actually very interdisciplinary. It doesn't stop with engineering, it also includes science, agriculture and biomedical field, and we call it as a comprehensive form of engineering. I am part of IIT&S and my research focused on polymeric nanofiber and catalysis. So since university is proud to have 3 world-renowned Nobel Prize level researchers, Professor Endo is a pioneer in mass production of carbon nanotubes. Professor Domen is internationally recognized for developing artificial photosynthesis using photocatalysis, and Professor Neva is famous for discovery of neutrino. Their outstanding achievements reflect the global excellence and research strength of our SINS University. This slide shows the pride of SINS University. Our distinguished professor, Professor Tesima, Professor Nagasawa, Professor Sugimoto and Professor Itsukim with Nobel Prize level achievement together with promising and rising star faculties shaping the future. We have also very famous figures in Japan as a specially appointed professors, Professor Akira Ikigami, Professor Kodaira and Ms. Mayu Yamaguchi. The person in the middle is the Olympic gold medalist in speed skating. So at SINS University, we actively collaborate with institutions around the world. Right now, we have more than 100 MOUs with international universities and research organizations, including IIT Delhi and CSR Apple Bhopal. Currently, we are also working towards collaboration with IIT Trichy and IIT Madras. And of course, I am very proud that we have just signed an MOU with TIT&S. I strongly believe this collaboration will be highly beneficial, particularly in promising student exchange, joint research, and research advanced in textile innovations. So I have a video on our institution. I'm sorry. So I will play the video at the end of the presentation. So let's begin my research topic on nanofibers. Actually, what is nanofiber? When you compare with the human hair, it is 1,000 times smaller than the human hair, extremely small size. So the nanofiber, it is a 1D fiber-like structure with a diameter of 50 to 500 nanometers with several orders of magnitude. In textile fabric industry, from 50 to 1,000, we can call it as a nanofiber in a nanoscale. So the nanofiber can be produced from polymers, metals, also from ceramics. These are extremely lightweight materials and highly porous materials. And the flexibility of the material is extremely very high and it can be easily handled. To produce the nanofibers, there are several techniques we can use to produce the nanofibers. Melt blowing, self-assembly, template-based synthesis, also hand spinning that we developed in our laboratory. And electrospinning is one of the very simplest and the easiest method to produce nanofiber. It is low cost. Recently there are developments in the mass production to produce the nanofiber. That is also one of the very big advantage of electrospinning. And less environmental pollution is also the key factor. So what is it? It is a technique that uses high voltage to pull the polymer solution into fiber. Here you can see this is the polymer solution and how the fibers are forming. In the next slide you can clearly see how the nanofibers are forming. This is the history. I will just skip this. This is the schematic of the top-down manufacturing process of polymer nanofiber. There are 4 important parts you have to note: power supply, electrode, and the polymer container, and this is the rotating collector. So this is the video I can show you, you can understand. So this is the polymer solution. When you apply high voltage, the polymer solution is get dragged into nanofibers. You see how the nanofibers are formed from the droplet of the polymer solution. The mechanism is very simple. When you apply sufficient high voltage to the polymer solution gets charged, and when the electrostatic repulsion counteracts the surface tension, the polymer solution at the tip of the collector, it will be stretched into fiber form. So eventually the solvent evaporates and the nanofibers are collected on the collector, metallic collector. So this is the instrument, laboratory scale single nozzle instrument. The polymer solution, when you apply high voltage, sufficient voltage, you can get the nanofibers. And this is the rotating collector. You can collect the nanofiber, and you can see it here. After collecting nanofiber, it is like a membrane-like form. And this is laboratory scale. We have only one nozzle. We also have multi-nozzle electrospinning machine. Actually, we developed this machine. We designed in our institute, and we have the mass production machine. This is the, you can see, multi-nozzle electrospinning machine.
Professor, how you solidify after a spinning process? How you solidify? How you convert in a film form? That what is that machine? With respect to temperature, or you are using some specific?
No, actually, when you after electrospinning, it eventually evaporates. Solvent will get evaporated, and the fibers are collected on the rotating collector.
Okay.
Then you have to, in case if you are using DMR, high boiling solvent, you have to dry it. In case of if you are going for acetone and low boiling solvent, okay, then you don't have to go for an additional drying process.
Okay. Thank you.
So in our laboratory, we have successfully fabricated various nanofiberic materials from polymers, like PVA. This is water soluble polymer, and in this case you have to do evaporation because this is water based solvent, and PVDF, PVAC, PVL, and in case of cellulose acetate we use mixed solvent like a DMF and acetone. In this case you need to evaporate the nanofiber in order to dry it. And also see, there are many polymers. The important thing is fiber without beads are very challenging. In order to achieve fibers without beads, you have to optimize the conditions like the polymer viscosity, conductivity, and surface tension of the solution. Also, when you process it, how much voltage you are applying to the polymer solution. That is also very important to get very uniform morphology. So without beads, these are very important. And this is the mass production machine we have developed in our institution, and recently we have with 1,000 nozzles. The mass production machine with 1,000 nozzles, and you can produce 60 meters in a minute. So not only the random nanofibers, you can also produce aligned nanofibers. Also the porous nanofiber, halopore nanofibers, porous nanofibers, twisted tipped nanofibers. These are just to, by controlling the speed of the collector, by using different solvents, you can get this morphology. So that's why the electrospinning is very simple technique to obtain various morphologies. The thing is, the polymeric materials are almost, we can say, inert. So in order to bring some functional property, you have to functionalize it, or you have to modify the surface to bring the biological or energy type of applications. You have to modify it. So whether it can be a covalent modification or non-covalent modification, or just the grafting of some bioactive materials to bring the property suitable for the application. So by modifying it, you can bring, you can tune the porosity, the surface area, and also you can change the hydrophobicity, hydrophilicity of the polymer, and also you can improve the mechanical strength, also biocompatibility. So So after modification, you can go for various applications, not only for a particular application. You can go for the filtration, textile, clothing, biomedical, even catalysis, sensor, and also for energy storage applications. So in our institute, we have 4 main teams: catalysis team, energy team, environmental team, and biomedical team. The catalysis team, they are developing catalyst material for catalytic application, and energy team, they focus on energy storage material by using nanofibers. And environmental team, they focus on some filtration, removal of toxic ingredients from industrial wastewater. And biomedical team, they are focusing on controlled release, and sometimes they go for wound dressing by using nanofibers. So our catalyst team has developed several nanofiber-based catalyst material for different catalytic applications. And some of the works are published in some reputed journals like carbon, ACS catalysis, carbohydrate, polymer, and so on. So in fact, the catalysis field is highly profitable. And you can see there are the top companies, they are focusing on the catalyst materials. The problem with the current catalytic materials are expensive. And they often use graphene, CLD, which are expensive, and sometimes they are toxic. So we wanted to replace the current industrial catalyst with our nanofiber system. So what we did, we took the biomass, cellulose material. So as you know, cellulose is widely available, and in chemistry point of view, you can easily modify the cellulose. If you convert it into nanofiber, you can easily modify the surface. This is the advantage, and low cost, as you know, and thermal stability is also very high. When you take nanofiber, you can modify the surface here. You can see, you can bring positive charge, negative charge, so that you can incorporate the desired materials to bring some property for application. So this is the experimental procedure. I can briefly explain this. We electrospin cellulose acetate nanofiber, then modify it with we deacetylate it into cellulose nanofiber. In fact, cellulose acetate stability is not that good, so we converted it into cellulose form. Then we modified the surface to bring the positive, negative charge, and then we coated nanoparticles on the nanofiber. So the thing is, when you go for chemical modification, you should maintain the morphology of the nanofiber. So you can see even after modifications, the morphology, the fiber morphology is intact. Okay, the 10 images you can see how uniformly the nanoparticles are coated on the nanofiber. And this is, in some cases, it is very difficult. And more importantly, how much metal, in case of metal composite, how much metal you are incorporating on the nanofiber without aggregation and with uniform dispersion. In our case, due to the surface modification, the nanoparticles are very uniformly decorated and also, so uniformly decorated, and the size is also very fine, so that the activity, the catalytic activity will be very high. So after the modification, after the construction of the catalyst, we applied it into some chemical conversion. This is one of the industrial important reactions. We applied for this reaction, and the yield is about 99%, and the selectivity is 100%. And also for the oxidation reaction, the catalyst was worked well for the oxidation as well. And the selectivity is very high, nearly 100%. The disadvantage is when you go for a harsh reaction condition, such as if you go for a basic condition and high temperature reaction, of course the cellulose is not that good for the application. So the same material we applied for conversion of nitrophenol into aminophenol because it is highly toxic. When you go for a textile industry, they often use this nitrophenol. So we wanted to convert this nitrophenol into aminophenol by using sodium borohydrate. Our catalyst method is highly efficient. And the good thing is you can reuse it multiple times. Even after 10 times, the activity still remains intact. And we developed electrode material for energy storage application as well. As you know, when you go for a flexible material, the power density, energy density is the challenging one for in the energy application. So we modified the electrode material to bring some unique property. This is the experimental procedure. We mixed two polymers, immiscible polymers, PON and PMMA, and we electrospun it. Then after stabilization and carbonization, we obtained multi-channel carbon fiber. When you go for single fiber, the surface area is lower. But when you go for multi-channels, the surface area is very high, and also the porosity will be very high. So we optimize the ratio condition to bring to achieve this multi-channel carbon fiber. You can see how flexible it is. So 10 millimeters, you can see it is when you the carbon fiber, it is around 200 nanometers, but the multi-channel carbon fiber, it is close to 50 nanometers. So this result shows the surface area, how it is changing. You see, with the carbon fiber, the surface area is 350 close, and the multi-channel carbon fiber is around 467. So the modification and the coastal structures are very important to bring the surface area and also porosity. So we did some preliminary testing to test whether the material can be suitable for the energy storage application. And when you compare the carbon commercial one, it shows very high energy storage capacity. And recently, to achieve high power density and energy density, we developed a coastal structure. The cross section is like a COVID virus structure, virus cross section structure. And the results, we are doing the research, and we are getting some very good results. We are going to apply for a patent and also for a publication. So our environmental team, they developed some absorbent materials by using nanofibers. So the cyclodextrin is one of the very good material to remove organic solvents from industrial wastewater. So we modified the nanofiber with the cyclodextrin material. In the previous case, we coated nanoparticles for the catalytic application. In this case, we modified the surface, covalent modification of the surface with cyclodextrin material. And as I said previously, even after modification, the maintaining the structure is very important. So you can see after modification, the absorption property, most of the industry, they use toluene as a solvent for their process. So in the waste water, you can find too much toluene content. So in order to remove the toluene, we use our absorbent material, nanofiber material. It is very easily handleable. Once it is absorbed, you don't need to go for a purification process, separation process. You can just remove from the wastewater. So we achieved around close to 80%, which is also very high. And also for radioactive pollution, radioactive pollutant, we developed PVA nanofiber with some functional materials, iron-based functional material. We incorporated into it and we cross-linked it in order to get high stability. Because PVA is water soluble, when you go for removal of some radioactive species from industry wastewater, the fiber will be dissolved. So in order to achieve stability, we cross-linked it. You can see this is a pure PON nanofiber, and inside there are the functional materials are incorporated successfully. And these are some spectroscopic results to confirm the successful cross-linking of PVA nanofiber. And this result shows the absorption is over 90%, and within 10 minutes from the the industry wastewater, when we use our material, it can be removed, CCM can be removed within 10 minutes, 90% of the CCM can be removed. So this is highly advantageous. And also for some biomedical application, we fabricated silica nanoparticle and we loaded with the drug on the silica nanoparticle, and we incorporated into nanofiber for controlled release property. So here you can see the profile. It is even after 100 hours, the drugs are being released. So this is very good for biomedical applications and also for wound healing, even for blood vessels. So recently, accidentally, we got some honeycomb-like structure by spraying green oil on the, during the collection of nanofiber, we sprayed green oil on the nanofiber mat, and accidentally we got this honeycomb-like morphology, and our students, they are investigating it and they are trying to repeat this, and once it is done, we will go for some biomedical applications. So these are some commercially developed, available product developed in our laboratory, nanofiber mask and food bags, even sanitary pads, also some air permeable nanofiber membrane which can allow only air to pass through and not the water. And recently now we are focusing on some industrial DAP filters which can remove toxic gases from the industry, and which is also under progress. So if I have time, can I play a video? Okay.
of Technology Delhi. Welcome, please.
Am I audible in the last row? I can see some students sitting in dark. Am I audible? Good. So, very warm good afternoon to one and all. Precisely, I have always given a post-lunch session. Whether I am lucky or unlucky, I don't know. But that is good. I want to keep you awake throughout. And I have sufficient time, so I will take around 30 minutes for presentation and then 10 minutes for question and answers, because organizers have given me around 40 minutes. So approximately that.
No 30 minutes, sorry.
Okay, so it is now
only,
30
only
minutes.
30 minutes.
Okay, so I will take 25 minutes for presentation and then 5 minutes for interaction.
Yes.
Okay, so topic I have selected is actually at the intersection of, if you talk about composites and functional textiles, because now people are also talking about functional composites, and without making a functional fiber or functional filler or functional resin, it is very difficult to make functional composites. So I will be talking about basics, and then I will try to correlate it with the theme of the conference. So topic I have selected is actually advanced functional textiles and composites for technical applications. Okay, so I think this is well known why textiles are important, what are expected out of textile materials, and now people are looking for quality and at affordable cost. That is good enough. But now what is happening is everybody is talking about functionalities. So we don't want textile as a basic need of human being, because many things are witnessed in recent past. If we know COVID pandemic, there are many things which are coming into picture. So people expect functional properties out of textiles. So like in this classroom, we don't need air condition. We want centralized cooling by textile materials. During winter, there can be textile which can heat us. So there can be different things expected out of textiles. So it's not a basic need of human being, we are talking about functional need. And we expect many things out of a very thin layer of textile material. When we construct a building, we have a very thick layer and a dense material to give certain properties. But in case of textiles, we have a very fine layer and we expect a lot of things out of textiles. So nowadays, the environment is not that friendly if you talk about ecological balance and all. So that's how it is becoming a functional need. And ecology is a buzzword. If you talk about anything, people are talking about sustainability, recycling of composites, recycling of coated textiles, recycling of textile materials. Yesterday, somebody was telling minimum 20% recycled material should be there if you want to export something to Europe. So that actually explains what we have done with this planet. So we started making garbage and making dumping grounds. Dumping grounds are exhausted and there is a mountain now, artificial. And people are constructing roads on this garbage mountain, and trucks are also moving. Can you imagine the strength of that garbage, right? So that is where we played with the planet in a wrong way, and now we want to recover back. So we want to actually reduce, reuse, recycle, and whatever things we have already done, we can take it from this only. Like if I have a garment, if I throw it, it may biodegrade or not. So there is a color, I can take color out of it. There is a fiber, so I can take fiber out of it and make a new product straight away. Nothing is required from industrial perspective. So this is where everybody is talking about profitability in terms of sustainability and protective things. And that is where we require all functional materials. Our lifestyle is changing, we are getting aware, we want protection. Most important is we want quality of life. So textile material we are wearing from morning till the night, right? All the time. So that is very important material in our life. So we want this material to give us a quality of life. And that is where functional textiles are coming into picture. Now this is very simple thing, how to design this shirt. Very simple, you can take a fabric and stitch it. It's a conventional textile. But if you want to design this, now cotton shirt will not work. You want high performance fibers, multiple layers, and coated, laminated, and so on. Many engineering aspects are coming. Then we move to this product. Product is technical textile once again, but the expectations are different. We require repellency against chemicals, protection against many things, water repellent, oil repellent, and so on. This product, again, technical textile, but the expectations are different because the environment to which it will be subjected is changing drastically. And this guy doing surgery, there can be cross-contamination from patient. So the expectations are different. So this is where we are talking about functional textiles, apparels, clothing, composites, all. Now for example, some properties like antibacterial things are there, flame retardant, water repellent, many functional properties are there. These are few examples just for understanding. So people want it to be antibacterial if some microbes are coming into picture, not all the time, but where protection is dominating comfort. In those cases, we want it to be antimicrobial. Insect repellent if I am going to a jungle, right, or if I am putting a tent in a forest and there are many insects. So I want that tent to protect me from all insects. Insect repellents or even apparels, and many more properties are there. If you talk about antimicrobial things, we have witnessed worst COVID pandemic and we know the effect of microbes on our health. Very important, they can play with the properties of textile materials, that is fine. Strength loss is there, color changing is there, that is okay, we can tolerate. But there can be infection from disease causing microbes, that is not acceptable. So in that case, we want antimicrobial things. There are many products which are supposed to be antimicrobial. Then comes the flame retardant. In case of fire accident, if you look at yourself, in this room, many things will burn. Wood will burn. Most important material that will burn is a textile material. Flammability is very high. It can be thermoplastic or it can be cotton-like material, but everything will burn. It can be with melt or without melt. So that's how we require the flame retardant textiles as well. Then there is also something called mosquito. So mosquitoes are causing very dangerous diseases nowadays. They were causing it early also, but new diseases are coming into picture. So in that case, mosquito is called the most dangerous kind of animal. If you refer this CDC website, they say mosquito is the most dangerous animal in the world. People die out of war, people died out of COVID pandemic, number is very less if you compare it with mosquito-borne diseases. So that's where this is also an important kind of research where we want protection against the most dangerous animal in the world, mosquito. So what we are doing in our research group, we work in 4 verticals. If you talk about, we are working in sustainable textile chemical processing, where we are making many enzymes, then water recycling, chemical recycling, combined processing and so on. Then second important area is functional dyes and chemicals, where we are synthesizing many chemicals. If you look at the colors we are using, if you look at the audience right now, almost 99% textiles used are colored, only few whites. That itself signifies the importance of color. So we are working in the area of functional dyes, where many products are there. We are making microcapsules as well, softeners as well, many products in this category. Then this is very important area nowadays, which is called coating and composites. So in this area we are developing many polymers for coating. We are doing FR coating, FR composites and many other functional composites. Then the last vertical is multifunctional textiles. In this case we are working on nanotechnology and natural dyes and many functional chemicals. So these are the 4 verticals where our group is working. I will start with the first, very important, which is called textile coating. and lamination as well. Here we have a textile material as one of the layer in this. We have another layer of polymer and one more layer of filler. So if you want to engineer this material, it is very simple. You play with the polymer or you play with the filler and make a fabric which is having all those properties. Let's take an example of very simple thing. If I want to make something X-ray protective, so you take a filler which is X-ray protective, put in the layer of polymer and put it, you land up with X-ray protective fabric. As simple as that. You have graphene, you have carbon nanotubes, you have many fillers which can be added, and you also play with the chemistry of polymer. So in our group we have synthesized many new polymers, functional ones. So in one of the works we have synthesized water-borne polyurethane. So water-borne polyurethane is very simple polymer. Polyurethane is the most important polymer in coating. You have used PPE kits sometimes. Most of the PPE kits are laminated with TPU films or sometimes coated with TPU. Now in this case, polyurethanes can be breathable. If we want comfort, it should be breathable. If we don't want comfort, everything is blocked, then it is non-breathable, non-porous. So what we have done in our lab, we have prepared a polyurethane which is actually by some process. This is a patented product and published literature as well. Now there are two problems in polyurethane. One, it is solvent borne, that is one, toxic solvent is used, and second, polyurethanes are not functional. So in this work we have actually targeted both problems. So we have made water-borne polyurethane, so water is used, and second, this polymer itself is antibacterial. So you just apply polyurethane on fabric by coating method, and then you will end up with antibacterial properties which are durable till this polyurethane stays on fabric. It's like a life of that coated textile. Then we have tested whether it is waterproof or not and whether it is breathable or not. So we have found the polyurethane layer is highly breathable. It gives us a hydrophilic path through which water coming from the body, vapors can pass through, but liquid water coming from outside cannot come in. So that is called breathable waterproof kind of applications. We found excellent water repellency. Then we also tested it in hydrostatic pressure test. 100 plus is a good hydrostatic pressure. Then moisture management was also there, so it can give you hydrophilic path, but water cannot penetrate on the backside. Then because it is antibacterial, we have tested it against S. aureus and E. coli. And what happened was the colonies were disintegrated. We got excellent kind of bacterial colony reduction in a simple coating. And the reduction was durable. We have tested it till 50 washes, nothing happened. So this is what we propose. It is a hydrophilic path through which the water vapors can pass through because they are nano, and the liquid water, which is a bigger droplet, cannot come in. Then the same polyurethane is modified to make it mosquito repellent. So polyurethane you just apply on the material will become mosquito repellent. And there was a tweaking in chemistry, we have some chemistry expertise in this. So we have tweaked the chemistry of this polyurethane and we landed up with a mosquito repellent polyurethane. This was coated on most problematic case cotton. So the cotton became antimicrobial as well, it became mosquito repellent as well, and there are liquid water and other things that remains intact. So we have tested UPF also. In this case we got excellent UPF rating along with all those properties. And remember, this is not a colored polyurethane, we have not added any TiO2 or zinc oxide, it is a simple layer of polyurethane itself, very simple. Then we have tested antimicrobial activity against S. aureus and E. coli. This is a 10 wash result, but we have tested it even till 50 washes, nothing happened. So from 95 to 83, and it went only till 80%, that remained constant throughout. Then we tested mosquito repellency because they are claiming it is mosquito repellent. We have tested it, and what we found was a single layer of this polyurethane gives 100% mosquito repellency. Mosquito will hate it, they will not sit, and you wash it whatever times, the repellency is maintained, nothing happened. Then we have tested weathering resistance because if the fabric is used for outdoor application, weathering is very important. UV light, rain, all kind of accelerated weathering is required. So we tested it, we found like the uncoated cotton is strength loss is there, the color is changed, but in case of coated, strength loss is not that significant and color was also not changed. So that gives us a good confidence in this product. Then we move to radiation protection. Like I said, we want protection from high energy radiations like X-rays, gamma rays and all. So in this case, we have added the filler which is there in this polyurethane, and then it is formulated and again it is coated on fabric. We have the coated layer with a filler, and then we tested all properties along with X-ray protection and gamma ray protection. And we found encouraging results. It showed excellent resistance against X-rays. X-rays are not allowed to pass, at least in an excellent range. And gamma rays, we got a good result compared to literature. So a single layer of this fabric can reduce gamma ray radiation by some percentage, which is much more than the reported products in the literature. And the product is generally multi-layer. So we don't use only single layer thin cotton fabric. So you can have multiple layers of these cotton fabrics, and then you have very efficient gamma ray reduction. So that is also achieved out of this. Then we doped it with graphene. Obviously graphene gives us EMI shielding and various properties, and we got all those graphene properties in this layer. Please don't record this, this is actually unpublished data in some cases. So then we have a very simple softener, which is silicone softener. All textiles are finished with silicone softeners. Like whenever textile mill is processing a fabric, last is finishing with silicone. Whatever it is, local product or export quality product, it is finished. So in general, these silicones are actually getting lost after one or some washes, maximum 5 washes, and it is not functional. So in this case, we have patented a product. What it do is, it is a very simple silicone, but it gives antimicrobial activity, it gives mosquito repellency, it gives fragrance, and it gives softness, which is hydrophilic. So if you put it on terry towel, you put water, it will be absorbed straight away, unlike conventional silicones which resist water penetration. We have tested all properties. Do I have 5 minutes? Okay, I will move quickly. So then we have chitosan, which is very important polymer. We use chitosan to make a colored kind of cotton, and this colored cotton is mosquito repellent, antibacterial and UV protected. Very simple process. You have to treat the cellulosic fabric with this, and this is treated with chitosan. You will end up with all these properties. Very quick process. This is also patented. Then in composites, because I am from textile chemistry background, I thought why not to use textile chemistry concepts of conventional processing in composites. So I found in composites resin is used. Everybody is using epoxy, right? And it is not flame retardant. So what I thought was, can I tweak epoxy resin? So we have synthesized new epoxy resin which is flame retardant. So you have to just put along with composite material, you will get inherent flame retardancy. Then now we are working on natural and recycled fibers based composites, where we are recycling fibers as well as polymers. So everything is recycled. And we are also working on functional composites, where we are synthesizing new additives for a composite material. Then I have my favorite area, which is actually dyes. So functional dyes, there are many functional dyes reported in the literature, but most important is mosquito repellent dyes were missing few years back when we started, and we found nobody is working on polyester, everybody is working on cotton. So we targeted all classes of dyes, disperse dyes for polyester, nylon and so on, reactive dyes for cotton and nylon, acid dyes for nylon, cationic dyes for acrylic. So we have covered all fibers in textile industry. And we synthesize mosquito repellent and antimicrobial dyes inherently for all type of fibers. Because technical textile is there, we talk about polyester and nylon mainly. So we made many dispersed dyes, yellow to red to some different colored. We applied it on polyester, and again we have mosquito repellency, antibacterial activity and so on. So it gives you color, it gives you mosquito repellency, and remember this is dye. So till the fabric is colored, the property will be there. Then we have tested bacterial colony reduction, UP operating and all, everything was excellent. We have tested toxicity because nobody is checking toxicity of products. So when, if by accident, if I throw this dye in a river, what will happen to aquatic life? So we found this dye is actually coming in non-toxic category. So toxicity is, forget about comparable with the commercial dyes, it is non-toxic. Then we have synthesized reactive dyes, cationic dyes. Then we have also synthesized polymeric dyes in this. Then we thought, can we have this flower and convert this into dye? Flowers will be wasted. So we thought, why not natural couplers? The leaves falling nowadays, can we pick that, convert it into a dye? Take this marigold flower, convert it into a dye. Polyester bottle, can I convert it into a dye which is flame retardant? So we started working on all waste materials and converted this into highly functional dyes. So we actually worked on many natural things, around 50 natural extracts were utilized to make mosquito repellent cum antibacterial dyes. Novelty of structure was checked. So there is no structure like this, all these are new molecules. They look very beautiful and they are highly functional. What are the innovations? The dyes are actually ready for commercialization. We are in process of technology transfer. All these products are TRL 6 levels, so industry can readily take it. These are some of the stalls which I have put. This is actually Swiss ambassador came into IIT Delhi, and our stall name was mosquito free zone. All products were mosquito free. There are many challenges nowadays which are now targeted. If you talk about, we are looking for multifunctional PVC. See, all defense applications are actually PVC coated fabrics are there. So we are making them breathable and functional. Then we want multifunctional polymer coating, fluorine free kind of systems like ever chemicals which we talk about, fluorochemicals which are not getting biodegraded, the biggest problem in the world right now. We are trying to get non-fluorine chemicals. We are trying to recycle coated textiles, composites, and we are also trying to recover chemicals from the waste materials. So that my presentation, I would like to acknowledge the funders, especially ANRF, Government of India, SERB, Ministry of Textile, DRDO, DST, IIT for providing funding, CRF for giving us characterization facilities, organizers for inviting me to give 30-minute talk, and my research scholars who work really hard, and the works they give me a good research results for presentation. These are some of the references. Thank you very much. We can't miss chemistry. Chemistry is everywhere. Even if you can't see it, you have to feel it.
Yes.
Thank you.
Your name and contact number. Any slide for your name and contact number?
In our program, and I would like invite after that next presenter, my co-chair Jasmine Kaur, representative next speakers after one questions with previous speakers.
Available, please.
Professor, you have given a nice presentation. Only I have a concern that how you pick the color from any waste material. What is the methodology you put?
So actually, see, these natural materials are rich in many bio molecules.
Yes.
Let's talk about polyphenolic compounds, flavonoids, and many things like tannins and all. So they are actually having some color which can have affinity for textiles. What we are doing is we are extracting it and reacting it with something else.
And pigment or something like
Yeah.
particular name is?
No. Actually, we are synthesizing a semi-synthetic chemical from a natural plus synthetic. And that gives us a concentrated chemical. Because if I take one marigold and second marigold, there will be variation in their biomolecule content. That is not acceptable in textile industry. So what we are doing is we are picking the molecules, standardizing it, reacting it, and we are getting a final product which is actually semi-synthetic, but it is actually concentrated. So there is a limitation of natural is removed, limitation of synthetic is also removed.
So that particular chemical is available which reflect or which avoid the mosquito?
Yes.
Okay.
We have synthesized many products. If you talk about NEET, optical brightening agent which we use to whiten the textile material, we have patented one optical brightening agent which is mosquito repellent.
Okay, great.
Just treat your textile material white for 5 minutes, make it mosquito repellent.
For like 5 to 10 washes?
Yes. And if it interacts, if there is a good dye fiber interaction, like dyes, then it will be there throughout the life.
Okay, great. Thank you.
Thank you, sir. Once again, thank you, everyone. A very good afternoon to all. I now invite Mr. Rajashri Sinha, NTTM, to hold the stage and talk about great scheme for startups in technical textiles. So please.
The great scheme of NTTM was launched in August 2023. So it is the one-of-a-kind scheme where we are promoting startups in the field of technical textiles exclusively. So by promoting the scheme, we came across a few ideas why startup was not coming up in the domain of technical textile. And we plotted and found out there were 9 reasons by which people were afraid of putting a startup. Either they are thinking that there would be a fear of failure, fear of judgment, what my peers would think after completing my graduation and not doing a job. What if my startup fails? Whether I would come back to the industry once again or not. So for that, we have introduced a scheme called GREAT, where we promote startup and we provide a fund of 50 lakhs for their ideas and innovations in technical textile. And we encourage them to pilot scale and further for commercialization. So the 4 pillars of this scheme are: first, to promote innovation; second, to facilitate commercialization; third, to strengthen the ecosystem and culture of startups in India; and fourth is to empower startups. As I've already mentioned, these 4 steps. Recently, we have encouraged a new wing of mentoring the startups to the top B schools of India like IIM. So if your project or the proposal which you venture out through NTTM, we provide you 50 lakhs funding for a period of 18 months, and before the closure of 18 months, just before the time for commercialization, we give you a free consultation and a guidance from top B school faculty members to validate your ideas and to scale up for the longer runs. So what is the eligibility of this scheme? So the basic eligibility that you need to be 21 years and above. You should have a bachelor's degree in any discipline. So we have few cases where we have seen people from microbiology also putting up a startup. So she was basically a startup. She was basically a research scientist in the BIRAC scheme. Now she has put up a startup in antimicrobial kidswear range, and we have funded him in that startup. So third, if you have already a startup, you can also apply wide, your age of startup company should be less than 5 years. And fifth, the person taking this scheme grant should be the major stakeholder in it. So if you have already a startup company and if you are applying in this scheme, at least you should have a 51% stakeholder in the company. And lastly, you should be associated with the incubator list which we have already given in the portal. So there are a few incubators like IITs, NITs, SERs and all other DST and AIC approved incubator list where you need to collaborate, get a letter of recommendation from them, and before you are finally approved, you have to sign a memorandum of understanding with them, and then you can kick off your venture. What are the do's for a good application? We have highlighted that first, you need to have this authorization certificate to be done. Now what is authorization certificate? Hypothetically, let's assume you are a startup company. You have two members in it. The second co-promoter or the promoter should authorize the person putting up a startup that he or she do not have any objection putting up a startup in this great scheme. Then we need the 10th mark sheet, educational details to be filled, and like you see, incubator details, like we have IIT Delhi, this startup. So he or she has to put a letter of recommendation from that institute body and submit in the portal so that they are collaborated with them during the time of the next 18 months of this scheme. And next, there are two ways you can put the application. This category of application is the place where you can put the startups, whether it is a functional prototype. So it is an idea where you want to validate the POC or the proof of concept. You just put up a functional prototype over there, or rather you have an idea, now you want to scale up, then you can select as commercialization of technology. Now the approval flow of startup. So first we put the startup proposal in the GREAT portal, that is the link. Then the proposal is initially scrutinized by the mission directorate team. If the mission directorate team finds the potential of your proposal worthy enough, then they move it to the EMC committee, this Evolution and Monitoring Committee. The EMC committee then approves the startup for the final body of recommendation, and is the EPC. This EPC is chaired by the Textile secretary herself. So once the project or the proposal is accepted by EPC, the startup is good to go. So till now we have funded 31 startups, out of which one startup, which I am going to show, Mr. Mukesh Kumar, who has already completed his proposal. So he has already got a funding from us. He is putting out some venture capital funding also received. He has signed a MOU with UP government for putting up his plant for the PM Mitra Park in Lucknow. So it is now your time to put up your startup if you want by 31st of March 2026. Thank you.
So if somebody is interested, how a proper handhold, because just in 10 minutes there cannot be...
So firstly, sir, you need to put up a proposal, validate your ideas, then you put up the proposal in this portal. The steps are very simplified. You just read the steps, go through them. There is a FAQ section over there. If you have any doubt, you can just reach out to us, reach out to me, and we can handle it.
And how to get associated, I mean in a very strong terms with an incubator?
So you first need to find the incubator who is related to the project. So if you have, so I don't know your idea. So if you are, the incubator can be of anything. You are given the freedom to choose your incubator. Now, if you are located near Bhiwani, this place, you can choose if IIT Delhi as your incubator or NITRA as an incubator. You just need to explain what you want to the incubator head. If he or she is convinced about it, they will provide a letter of recommendation to you. That letter of recommendation you need to attach in this portal. while submitting the application. After submitting the application, we review it. We have a 3-step process where mission director reviews it and then goes to EMC and then EPC.
And final question, that as there is a lot of scope in textiles, how to find a relevant one which this can be scopeful, this as a startup?
Relevant in which sense? Relevant can in technical textile. So your idea, like you can, like Dr. Javed has given up a presentation of mosquito repellent. If you have an idea of mosquito repellent and you want to commercialize it, you can straight away put up the commercialization startup over there. You highlight the objective, the novelty, your scale-up plan in the upcoming 18 months, your milestones. Based on your milestones, we fund your money, and during the time of commercialization, if you need help, we handhold you to get connect with the UP government for the MOUs signed up for the PM Mitra Park as well. Okay. Thank you.
Thank you. The get certificate. Maya Krishnan Gopi Raman, welcome please.
Okay.
Next speaker please, Javed Sheikh.
Yes, sir.
So we thank you all participants for this session and moving to our next session.
For the next technical session, which is conducted in LT1, you may please go there. For the technical session, LT1, all the participants who are registered there. Thank you.
I am Dr. Vatan Serawat from Government Engineering College, Rewari, and I am here to present on the topic Embedded Sensor Networks in Textile Composites. So now is the era of digital world, so basically everything is going to be digital, and so as with the advancement of textiles, now the fabrics are being prepared, developed and manufactured with the technological evolutions. That means we are in the era of sensors now. Everything is being sensed by different kind of sensors in our surroundings. So basically the concept is very simple and straightforward, that we are building the fabrics which are embedded with different kind of sensors to sense different kind of activities and phenomena or scenarios through the surroundings. So just like we are using in present world where we are using different kind of digital devices, now this is a new advancement where the digital devices are being fabricated into the fabrics or the clothing itself. So it becomes a more effective and efficient portability of the digital devices, where you can equip your clothing with different kind of sensors to sense various kind of stimuli related to individual person or related to any kind of particular department, specifically in the health departments where various health related issues can be diagnosed and predicted with the help of sensors through the such kind of technology. So basically the main advantages of these kind of technologies where integration is being done with the sensors with clothing is comfortability. Now as textile composites is a new kind of innovation where general textures of the fabrics are being mixed up with various kind of like metallic materials or synthetic resins. So these provide extreme level of comfortability to the wearing person. Another one is lightweight design. Textile composites, when integrated with fabrics, makes the overall the concept of the fabric is in a lightweight approach, where comfort and portability is the main advantage. Then seamless integration. Sensors, because this provides a high strength to the fabrics, so the sensors can be integrated with the fabrics very effectively and efficiently. Then durability. The composites provide enhanced durability to the fabrics for a longer lasting approach. So this is the basic architecture of cyber physical system that we embed in our textiles, in our fabrics. That is divided in 4 layers. First one is the physical layer, where actual sensors are being affixed into the fabrics, where they sense different kind of activities and communicate the information to the next level, where the next layer is your communication layer that provides the communication between the sensing nodes to the processing node, where the information that is collected through the sensor nodes will be processed at a central level. Then there is a processing layer which will be processing the information collected through the sensor nodes and will provide various kind of insights so that the better and effective decisions can be taken for the further actions. Then comes the application layer. Application layer basically a cloud platform where the insights generated through the processing layers are implemented and some decisions are being made and some better and efficient control mechanisms or actions are being generated so that efficiency or performance of the system can be enhanced or improved. Then some kind of sensors that we generally embed with the textiles are temperature sensor, basically to monitor the body heat and environmental conditions so that we can use such information for specifically for healthcare and climate control purposes. Then comes strain and pressure sensors, which detect the movement and posture and pressure distribution for specifically for sports persons, where extreme level of pressure is there on their body and mental health. So such kind of sensors can detect the pressure at a very initial phase and rectifications can be taken timely. Then comes biometric sensors, where the biometric sensors can track the heart rate, respiration and vital signs continuously so that remote patient monitoring and fitness tracking can be achieved. Then comes moisture sensors. Moisture sensors basically are used to identify the sweat and water or chemical presence, specifically to identify the hydration level, whether the particular person is hydrated or it requires some kind of liquid nutrients for the body. Then there are some communication technology that makes this concept very effective, as these are the portable technologies which require the amount of power and durability, and for that we require such kind of technologies which require less power to communicate the data between the devices. So first one is Bluetooth low energy, ultra low power wireless communication, which enables the sensors to work not for the days but also the weeks, because these require very less amount of power to work for longer period of times. Then second option is energy harvesting. Basically the inclusion of solar cells and piezoelectric fibers into the fabrics makes the capability of the fabrics to generate the power itself through the fabrics, through the body heat and the movement of the body, so that some amount of power can be generated there itself and can be given to the sensor nodes for effective functioning. Then miniaturized batteries. These are the very small sized batteries which can be affixed in the fabrics itself without compromising the comfort and flexibility of the fabrics when you are wearing it, and which can be used for to enhance the durability of the sensors while they are performing. Then another term is coming there is the on-board computing or edge analytics. Basically, edge computing provides such kind of scenario where the sensor nodes where collecting the information are generating the insights there only. That means there is no requirement of communicating the information collected through the sensor nodes to the processing layer, because these provides embedded processing units itself into the fabric. So whatever the information is collected through the sensor nodes, that will be collected over there only and will be processed at the edge level only. That means where the sensors are deployed, at that level only information will be processed and insights will be generated. So basically it will provide the mechanism to save the power consumption into the system, because the power that is required to communicate information from sensor nodes to the processing layer, that will be omitted because information is processing itself at the edge level. So that is a new concept where less amount of power is required to process the information into the scenario. Then this is the real world impact, the basic applications. The most significant application of embedded sensors into the textiles, into the fabrics, is in the healthcare monitoring, where continuous monitoring of a particular person or patient is required. So if the patient is wearing such kind of fabrics or clothing, so 24/7 monitoring of the patient can be achieved with these kind of technologies. And suppose the patient is there in this ICU and we require a lot of machines to be connected to the patient. Now that thing will be omitted here. The patient just need to wear such kind of technologically enabled fabrics, clothings, and there is no need of extra machinery to be connected to the patient physically. Then in the sports performance, where sports is a very vital area in which the sports person need to be monitored at each and every level, because a lot of energy is being used by the sports person for doing various kind of physical activities, and it requires a continuous monitoring of the particular sports person. So for that, in such kind of fabrics can be used for the sports dresses or the costumes, and can improve the efficiency of the particular sports person and the event itself. Then industrial safety. Basically, lot of industries use chemicals for various kind of products to be developed in the industries, and for that kind of scenario, we require a safety procedure to be implemented, because it is a very hazardous condition or situation for the people who are working in such kind of chemical industries. And if we are using such kind of technologically enabled, advanced sensor enabled clothing or wearables for the wearable dresses for the working people in the industries, so they can be monitored continuously, and if any kind of hazard is being initiated in their body, then that can be monitored and evaluated at the very initial stage. And there are some challenges or future directions that are specific in this area, that is the miniaturization, because we are embedding the sensors into the fabric itself, so it requires a very compact size of the sensors. That is, the microscopic sensors are being used for such kind of technological enablement. For that, miniaturization is required at a very high level to implement such kind of technology very effectively. Next is durability, because ensuring a long-term performance from the sensors, we require power, we require a particular effective surrounding environment conditions where sensors can work with efficiency and accuracy. Then AI integration. Now is the era where AI is being implemented and embedded in each and every aspect of the life. And AI, and if we are talking about the embedded sensor networks in the fabrics itself, Then for better processing of the data and better insights, but to generate better insights from the data collected from the sensors, AI has to be incorporated in such kind of networks, so that maximum efficiency and utilization of the resources, digital resources, can be achieved. Then comes security and privacy. As the technology gets into the general life culture of the human beings, as much technology gets introduced, more technology, more risk of the privacy and security. So that is the main concern, because if we are wearing the technology 24/7 with us through the clothing and fabrics, then we require some standard and advanced safety and privacy mechanisms to be implemented, so that the privacy may not be compromised through the such kind of technologies. So basically, if we are talking about the embedded sensor networks into the textiles, then seamless integration is the main concern that we should be incorporating into the fabrics. That means if you are wearing a normal cloth and if you are wearing an embedded sensor network, sensor clothing, then there should not be any difference while you are wearing it in terms of comfortability, in terms of relaxability of the particular person who is wearing that. Then comes real-time intelligence. Real-time intelligence means if you are using the edge computing, then the data is being processed at the node level only. So the information that is collected at the sensor nodes itself will be processed there only, and so that the maximum utilization of the information can be achieved in real time, because no transmission time will be required in that. Then comes transformative impact. That means if we are the technology is being built in our general culture, general day-to-day life through the clothing or through the textiles, then it should be very transformative. It should be capable to be implemented in various kind of aspects in different scenarios, like healthcare, sports, medicine, industries, like that. So this is all. Thank you very much.
Okay, Mr. Sherman, I have a question. Yeah. Okay, I have seen in your presentation sensor. How is sharing dates to my mobile or to my cloud? How will be sending dates from this sensor?
So that
because how I got the...
So basically the sensors are connected through the wireless technology mediums that are connected through to the processing layers itself, where the data is being collected through the...
Okay, and if I will be take for my TIT&S, therefore I will include to your clothes for everything, and getting these dates. Therefore, it will be sharing by GCM, or which system it's creating in this sensor for sending to, I don't know, to Europe, for example.
So basically, when the processing system can be placed at any geographic location, but it will be connecting through the internet through wireless mechanisms. It can be voice or LTE, or it can be Bluetooth enabled energy, where it connects to the nearby device, and then that if it is internet enabled, it will be communicating through the IoT Internet of Things.
Through IoT of Things, it can be sending.
It can be communicated.
And, how many dates it will be sending? Because it can be depend how will be time. And
that will depend upon the memory, on the power capacity of the individual sensors. For generally they work from days, 2 or 3 days to weeks. For example, 7 to 10 days around. It is a standard operating time.
7 to 10 days, and
after that they will be required to be recharged. Their batteries need to be recharged, and then they will be continuously working again for the next period of time.
Okay, and second question about accuracy for this sensor. How was tested and analyzes this accuracy for different textile, different clothing?
Actually, accuracy is is the technological concept of sensors. Sensors are being designed where they collect the information from the environment where they are generally deployed, and these sensors collect the information generally precisely from the surroundings itself, because there is no criteria of distance in the information collection. So
because it's depend how the humidity, wet, how temperature.
Yeah, it will perceive the environment in which what environment they are operating. They will sense that kind of, for example, if it is a temperature sensor, it will sense the amount of temperature that the sensor is deployed in, and if it is sweat or water.
This sensor I wanted to try for testing because I have problems sometimes with different countries and testing different clothes because there is different humidity, different temperature, different.
Yes. So that's the main purpose of such kind of technologies, because they perceive the surroundings of the environment, and because environment is different at different geographic locations, different countries have different climatic conditions, so that so when the sensors are deployed in the particular environment, they will sense that data, and the data will be collected by sensors and will be communicated to the processing layer, and where the data will be processed and will be analyzed, that what kind of data it has been collected and what are the necessary actions that we can take upon that data we have collected.
After must be sensor some updated.
When the data insights are generated, they are processed for the betterment in the near future, because the new technological updates have been are to be deployed into the sensors and the technology, so that when next time the sensors are working, they are working in a better way.
Yeah. Thanks.
Anyone else?
Thank you, sir.
To mitigate the microplastic generation. So as we know, the geotextiles are very familiar in the infrastructure nowadays, and from the last 2 days, so many lecture has been discussed about the geotextile, their benefits. So for the sustainable infrastructure, the geotextiles are very, very important. But I just want to highlight the other parts of the infrastructure development, that it causes certain environmental issues are there. When we are using the geotextile material into the infrastructure projects, then there are the limitations that the microplastics are also generated during its applications. So as we know, the market growth and environmental drivers is there for the geotextile materials. Why it is more popular? Because the geotextile synthetic is growing 5 to 8% annually. Infrastructure projects increasingly adopt the geotextile for the drainage, filtrations and the reinforcements. The usage of the geotextiles are increasing because the CO2 reduction is very, very large. That is safe for the environment. Also, the GHG gas and emission is also reduced by greater than 90%, and also the non-renewable energy usage in the geotextile projects is reduced by 80%. But the other part is there, that when we are using the geotextile materials, there is the release of the microplastics, and that is very hazardous for the environment. So microplastic contamination from the geotextiles remains unquantified. So there is very limited studies that how much the microplastics are generated and how they are causing the pollutions to the environments. No standard test method exists for measuring that how much the microplastic is released by the applications of the geotextiles. And infrastructure life cycle span is around 25 to 100 years. So they would pollute the environment and generate the microplastic in its whole life. You can say from the 25 years to the 100 years. And it is not from the 25 years. When we are starting the laydown of the geotextile material, the microplastic pollution would be started from the first day. So what are the geosynthetics? I think that has been discussed very nicely by previous speakers. The geosynthetics are used for the filtrations, for the drainage applications, for the separations of the two layers, and for the reinforcements. So it would give the strength to our projects, whatever the projects we are handling. The microplastic, now what is the real threat for using the geotextile materials? Geosynthetics are significantly but largely overlooked source of terrestrial microplastic pollutions. So very much research has been done for the water pollutions by the microplastic. But terrestrial microplastic pollution, that is the pollution created in the soil, that has been very limited study has been done, and no regulatory framework exists for measuring the microplastic pollution in the soil. So how this microplastic pollution is generated due to the use of our in the geotextile materials? So it is caused due to the three ways. One is called the soil sink effect. Soil sink effect, when we are starting or lay down the geotextile materials, from the first day the microplastic release has been initiated because of the abrasions, because of the pressure that is applied, and the microplastic that would be released, that would be just start build up from the first day of its applications. Another is the hidden pollution pathway. Hidden pollution pathway means, so whenever during its usage the environmental, like the UV rays would just fall onto the geotextile material, it degrades the geotextile material, and another microplastic would starts to initiate from the geotextile materials. Infrastructure scale risk, as we know, day by day the infrastructure is developed to the very fast rate, and whenever the infrastructure is developed, the geotextile material has been used to the large levels, and that would lead to another way of increment in the microplastic generation in the future. The fundamentals of the geotextile, that is again has been discussed to the larger extent. So it is used in the geotextile materials for the geogrid, geomembranes, geocomposites, tubes is also there, and the geonets and geomats. So we can just move ahead. So these are the different geotextile materials or the geosynthetic materials that are used in various applications. So that has been also discussed very nicely by the previous authors. So we can move ahead with that. Now how the geotextile material is manufactured. Generally the three ways are there where the geotextile materials are mostly manufactured. Non-woven, wovens and the knitted. But the knitted application is very limited for the geotextile materials. So mainly the geotextile material, either it is the woven geotextile or it is the non-woven. And mainly the non-woven is at the higher percentage of the geotextile materials. So how it is manufactured, the woven material would be first, this is the simple way we are dealing with the textile students, so they know how the woven product is manufactured. So generally the man-made fibers are mostly used in the geotextile materials. So fiber would be extruded, then it is drawing, then the interlacement by the weaving process, it is, and then some finishing treatment can be given just to reduce the or you can say just to add certain values to the geotextile materials by certain chemical finishes to the fabrics. Another way is the non-woven geotextiles. So non-woven geotextiles are manufactured by the different techniques, by the spun bonding, so where directly the fibers are extruded, intermingled and just made into the fabric by the heat. Needle bunching, where with the help of the needles we give the strength to the web. Thermal bonding, where the staple fibers are just interlaced with the help of the bonding at certain heated points, or the chemical bonding. So these are the different ways that we are manufactured the non-woven geotextile materials. So different type of the raw material that we are generally use: polyester, polypropylene, polyethylene, polyamides, or the natural fibers. So if you just go through the tensile strength, so this is just a comparative table of the different materials that are used. And about the properties, I think very much the audience are aware that the tensile strength would be considered to be the best for the polyester material. PET materials. Creep resistance is also better for the PET. UV resistance is also better for the PET, but it is the poorest for the PP. So wherever we are using the geotextile material made up of the PP, then the UV degradation is considered to be the fastest. So if you are using the PP material, we just go for certain treatment so that the UV degradation would be reduced. So we will talk about that in further slides. In case of the polyester, alkali resistance is considered to be poor if you are considering the pH greater than 10. So for that we have to consider about the usage of the polyester in alkaline media. Biodegradability. So here is the main issue that whatever the synthetic material we are using in the geotextiles, so they are not biodegradable. So this is the biggest disadvantage of using the man-made fibers for the geotextiles, and nowadays that's why the many products are launched with the usage of the natural fibers for the geotextile materials. Cost-wise, the polyamide is the costlier, so very little usage of the polyamide material in the geotextile. Only where there is the chances of high abrasion is there we are recommending the usage of the polyamide material for the geotextile material. But generally, geotextile materials are either they are used for the PT materials or generally PP. So now, generally on the basis of the property what the different fibers possess, so we have slight recommendations, or generally recommendation is there that the polyester is generally used for the reinforcement because it is the strongest, and for the reinforcement applications we are looking for certain strength into the materials. For the filtration and separations, PP is considered to be the better. Polyethylene, liner or the containments. So where we are just use the water containment, so we are using the PE materials, polyethylene, polyamide as I have mentioned where high abrasion is required, and natural fibers, geotextiles where the biodegradability is the main issue. But here the life is the only issue, so the life of the product that would be slightly reduced. Now how the microplastic is generated, so this is our main point of the talk today. So microplastic is generated in the three ways. So one is during the installations damage. So as you are starting the laydown of the geotextile materials, our microplastic release would be started. So how it is starting? Aggregate abrasion during the compactions. So whenever a geotextile material is laid down in the road and we are going for the compactions of the dirt and the stone particles, a force is applied. Due to that, there is the leaching of the microplastic from the geotextile materials. Or maybe the fiber cutting by some abrasive material that is applied during the road constructions. Dynamic trafficking over the laid geotextile. Whenever the road would be just completed, then due to the traffic load also the microplastic would be released. So the immediate and the largest source of the shedding is the immediate. So whenever we are initiate the lay down of the geotextile materials, our microplastic release would be started, and this is the biggest source of the microplastic generations. Second is the UV photooxidations. So whenever the PP materials is exposed to the sunlight, then UV degradation is started. So UV rays that just give the chemical breakage of the bond of the PP material, and during its whole life that would be the release of the microplastic would be there. Oxidation, so that would make the materials embrittlement and the surface cracking, free radical oxidation. So this is generally happen. UV problem is mainly in the PP materials. So if we talk about the polyester materials, there the issue is the hydrolytic degenerations. If the polyester material would face the alkaline media greater than pH of the 10, then the oxidation is happening, the polyester, the bonding that is breaking down, and the tensile strength is going to reduce day by day, and that starts the leaching of the microplastic from the surface of the polyester material. So these are the three ways that how the microplastics are released during the usage. Another is the leachate exposure in the landfill applications. So whenever the geotextile material is there inside the earth, so we have the different type of the chemicals, whatever the garbage is there, waste is there, when the water is in contamination with that impurity present, certain type of the liquid with the gases are generated, so that gases are going to degrade the geotextile material. So that is considered to be the leachate exposures. Biological is also there. There is the chances of that. The biologically there is the generation of the microorganism, fungi is there. So that would just also degrade the geotextile material is there. So these are the different ways that how the geotextile materials would starts to generate the microplastics. So installation damage that we have just talked about. So this is the largest microplastic source. 90% of the shedding is just happen in the first year of the application of the geotextile material is there. So we have just mentioned that needle punch non-woven most vulnerable for this microplastic generation is there. So that's why needle punch non-woven is considered to be the least if you have the concern about the microplastic regeneration is there. So if you give certain cushioning materials during the laydowns, certain soft sand onto the geotextile material below and above, so we can reduce this generation of the microplastics. So if the direct bigger stone particles would make the contact with the geotextile material, greater chances of the microplastic generation would be there. UV photo oxidations, if you just see the image for the PP materials, so this is the most dangerous part that due to the UV rays, the degradation would be happens. So just to avoid the UV degradations for the geotextile material, we can enhance by certain chemicals. So if there is a comparative chart that has been shown, if there is no stabilizer is added, so only the 15% life you can consider. And if we are just adding the amine type of the stabilizers, it can reduce the microplastic generations. Another method of just reducing the UV effect is the carbon black. If we just treat the fibers with the carbon black, the coating would be made onto the fibers and then the exposure to the UV light can be reduced. And if you can give the both by the carbon black and along with the HALS, so the efficiency of the product would be much increased. So chemical degradations, hydrolytic, we have talked about if the alkali media would be given to the polyesters, then the degradation would be faster. Latex we have talked about, so we can reduce the exposure to the polluted water, biologicals. So these are the different types, long-term field evidence. So jitna time ke saath, the longer would be the time, the leaching would be started. So these are the different type of the structure, needle punch, spun bonding, woven. So we can just move slightly faster. So this is a comparative assessment of the different type of the structures and their capacity to release the microplastic. So needle punch non-woven fabric is considered to be the poorest, and it is the most vulnerable to the microplastic generations, and the best would be considered is the woven material. So wovens are considered to be the best because the leaching of the microplastic would be reduced by the usage of the woven materials. So this is the life cycles. So life cycle means if we are mentioning that the geotextile material would be sustained for 25 to 100 years, but I have already mentioned that the microplastic generation would be started on the first day. So whenever the laydown is initiated, the microplastic starts the release. So this is the lifetime and the different phases that how the microplastic are generated. Environmental effect. So we can slightly move faster, we can skip that part. So what would happen with the chemical, so whatever the degradation would be there, the tensile strength would be reduced, drainage capacity would be reduced for the geotextile material. If the microplastic layer would be formed, tensile strength loss is there, filter performance would also be declined because the main usage of the geotextile is just for the, in the road construction is the filtration. So that would also be reduced. Now environmental benefit I have already mentioned that it reduced the gas emissions to the very larger extent. GHS would be reduced, carbon dioxide would be reduced, energy would be less used in the geotextile, but the problem is the microplastic pollution. So that is the main risk. Now what we can do, how it can be reduced. There are the three strategies that has been told. One is the manufacturing. Manufacturing means you choose the structure that would leach the least microplastic. So the best that would be considered is the woven product. So the woven geotextile is considered to be the best, where the chances of leaching would be less. Another is if the UV radiation is there, we can treat with certain chemicals like the HALS, like the carbons. So that would also reduce the microplastic generations. Another is the site protocol. Protocol means UV exposure should be very less. Force that would be there onto the geotextile material handling, that should be reduced, so that the microplastic generation should be reduced. So polyester and polypropylene, polyester mainly the hydrolysis is the problems. So we can treat with certain chemicals so that the life can be reduced. Polypropylene with HALS or carbon we can improve. We can engineering designs. So engineering design we have already mentioned, where the life is important, we go for the wovens. Though the cost would be higher for the geotextile material, so we can choose the different structure for the different applications, like the railway, we can use the woven monofilament, road base, we can use the woven slate fill, and for like the landfill drainage, we can use the geocomposite. Site protocols, so we have already mentioned these points. Okay, you can future framework. Now, what is the current test measure? So we don't have any test measure that can just study the microplastic measurement, how the microplastics are generated, what is the size of the microplastic. So we can design certain standards that can measure how much the amount of the microplastic would be generated and what is the size of the microplastic that would be generated. So some strategy for the abrasive test is suggested. So if this can be made the standardized, so that all the future geotextile material that should be tested on the basis of these parameters, so that would be fruitful. Okay, so these are the final points that we can take into considerations for just to reduce the microplastic generations. So installation damage is the largest, so we just make certain protocol how it should be handled at the first stage. 3-pillar approach we have already mentioned: manufacturing designs, manufacturing innovation, engineering design, and the site protocol that should be managed. Needle punch, non-woven are the most vulnerable, so their usage can be minimized. Or if the PPs have to be used, we can go with certain stabilizers. Some standard test methods should be suggested so that we know how much the microplastic would be generated during its use. And geosynthetic can and should remain a cornerstone of the sustainable infrastructure, but only if the microplastic pollution risks are quantified, regulated, and minimized through the major protocols. Thank you. Thanks a lot.
Thank you very much. And next presenter is Rachel.
Good evening to all. So, audible to you all, please? Okay, so after tons of rescheduling, so finally I will be presenting my research in this conference. So today I will be giving a short presentation on my one of my PhD's work. It is synergistic enhancement of interfacial bonding in metal-faced 3D woven sandwich composite panels. So this study, I am doing my PhD under Professor P.K. Behra and Professor Javed Sheikh. So our lab is Focus Incubation Center for 3D Weaving and Structural Composites. So Professor Behra has already briefly told about our lab and the facilities there. So my topic will be on sandwich panels. So the sandwich panels, they are the special type of laminates that are lightweight and have two face sheets and a lightweight core embedded in between them. So it's a 3-layer material system. One is face sheets, they are provide strength and stiffness, can be metallic, composite or ceramic. The core, usually thick and lightweight, primarily can be classified as solid or hollow. and then the most important part of is adhesive interface. So this interface ensures load transfer between the phase sheets and the core. So the key takeaway is stronger skins but lightweight core. You can have a high performance composite material with minimum weight gain. So sandwich panels. So this is basically a theory of sandwiches where the very much less, if you assume the material has to be 1, so if increase in weight, very minimal increase in weight, you can specifically increase the stiffness and flexural strength just by increasing the thickness of the core. So the primary objective of making sandwich panels is for making high stiffness to waste ratio and high strength to weight ratio, particularly in the bending tools. So sandwich panels are classified as based on phase sheet materials, can be metallic phased, composite phased, and then based on core we have solid core sandwich panels, primarily FRP cores, and then cellular cores, primarily foams, honeycombs, truss, corrugates. So solid FRP cores can be UD, 2D, 3D, woven fabrics or polymers. Hollow structures, you can see honeycombs, corrugated cores, truss cores, foam cores. So they are widely available and highly researched area. So these two types of sandwich panels, they have their specific properties and applications. So solid core sandwiches, sometimes referred as FML sandwiches, so they are used in applications where high fatigue and fracture toughness are required. And the hollow core sandwiches panels, as we all know, these are used for excellent impact resistance and they have very high strength to weight ratio. So if we talk about sandwich panels with solid FRP cores and metal faces, so here the metal face sheets, they provide the ductility and toughness to the structure, and the composite cores provide fatigue resistance and flexural strength by sustaining the shear loads. So superior fatigue characteristics can be achieved along with higher specific stiffness compared to conventional composite laminates. So I am using 3D woven cores as the core material. So already in the morning sessions you have listened to Professor Behra and Dr. Soumya. They already have a brief talk about 3D woven structures and their high delamination resistance, impact damage tolerance, and interlaminar fracture toughness properties. So these fabrics can be tailored according to your particular application in sandwich panels. The interfacial strength of sandwich panels is the most important part. So this layer is basically is the intermediate between your core and metal. So it can be fractured by using. It has two failure modes. So one can be cohesive failure, in which the adhesive itself fails, and then there may be adhesion failure, where the bonding occurs, particularly in the metal during with metal phase sheets. So this is mainly due to oxide layer formation on the aluminium phase sheets. So we can characterize this by using lap shear strength, and the interfacial strength can be improved by techniques using surface modification on the aluminium phase sheets, or by integrating nanofillers into the adhesives, or both we can use. So coming to my research, so I will be showing some of my results from this session. So my research workflow will be, so first I will optimize the nanofiller modified adhesives, then move on to chemical treatments on the aluminium phase sheets, then we perform some lab shear and optimization, and then flexural analysis and characterizations. So materials I will be using, the core is made from glass, it is 3D woven glass fabrics, orthogonal. The metals are aluminium 6063 with 0.5 mm thickness. So I am using epoxy resin and methacrylate adhesive, Flexus. So all sandwiches are prepared by hand layup method. The face sheets are sanded and degreased. So this varies with the modification. So it is basically the base process I explained here. So the nanofiller concentration we kept is 0.1, 0.3 and 0.5% volume, and sandwich dimensions are mentioned here. So nanofiller are reinforced using acetone and ultrasonic dispersion of nanofillers in acetone, and then adhesive, and then mixing until the evaporation. So it's basically a standard process. We use this process to make nanofiller reinforced adhesive for both carbon nanotubes. So basically we have used multi-walled carbon nanotubes. I forgot to acknowledge here. So we have used two types of nanofillers. One is multi-walled carbon nanotubes. Another one is graphene nanoparticles. So we used three types of surface modifications in this study. So first is etching. So we used two different types of etching. FPL etch, that is Forest Products Laboratory, using sodium trichromate and sulfuric acid. Second one is P2 etch, using ferric sulfate and sulfuric acid. So the alkaline treatment we then etched and then immersed in distilled water and heated for some time. So again, we also used anodizing on our aluminum face sheets. So the process is very simple. After degreasing and alkaline etching, we immersed in 0.2% of NaOH, and then specimens were anodized in phosphoric acid for 30 degrees Celsius, followed by rinsing and drying. So we used ASTM D7250 to assess the flexural performance, and for flexural fatigue we used ASTM D7774. So we took the 70% flexural strength as for fatigue. The R ratio is 0.1 and frequency is 2 Hz. The span to thickness ratio in both cases were 16:1. So these are some micrographs you can see. So the first one here is the sulfochromate etch. So here the and in the center one you can see this is ferric sulfate P2 etch, and the last one is anodized samples. So the anodized samples you can clearly see the deep micro pits pores and enhancing the interlocking. So I will be explaining this phenomenon later. So the oxide layer is created more deep micro pits in anodizing samples as compared to first two etched samples. So all these three methods have their limitations and advantages. So the first one, which was historically used, is now not used in commercialized because of some toxic effluents. So the center one is the alternative for FPL etch, is widely used nowadays but have limitations in some strength. But the last one, anodizing, provides very high interfacial strengths, but often the limitations are it's very complex with very high processes. So coming to the results, in the first graph here you can see so you can see the single lab shear strengths and flexural strength for all four, that is sanded, that is control sample, FPL etched, P2 etched and anodized samples. So obviously the results have shown the anodized has the best interfacial strength and flexural performance, followed by P2 etched and FPL etched. So based on for our future testings. So we also find out the effect of nanofiller loading on the lab shear strength of sandwich panels. So the nanofiller optimization in sanded aluminum shows an optimum near 0.3% volume. Sorry, it's not weight percent, it's volume percent. Sorry about it. With about 10 to 12% strength gain in both CNT and GNT nanofillers. So this data provides a baseline period to our combining nanofillers with P2 and anodized surface treatments. That's for sake of synergy. So coming to our next results, so this shows the lab shear strengths for aluminium surface treatments along with nanofillers. So for both CNT and graphene modified systems, anodized samples showed highest joint strength followed by P2H samples. So this is attributed to very porous anodic oxide formed on the anodized aluminium samples, which enhances the nanomechanical interlocking. So these are some micrographs showing the lab shear fractures for PAA anodized samples with CNT modified adhesives. So in the first case you can see with 0.1% volume percent or for CNT you can see bridging is observed within anodic oxide pores, which is indicating insufficient network formation of the pores. At 0.3% you can see dense cohesive morphology with extensive CNT bridging, and at 0.5% volume you can see the amalgamation occurs, creating a heterogeneous adhesive oxide interface near the lab shear joints. So we try to analyze the synergy between surface modification and nanofiller for lab shear. So here you can see if we compare with the sanded samples, the lab shear is high for only modified samples. However, if we used nanofillers, the strength increased very much. So about 124% strength was observed in anodized plus 0.3% volume CNT nanofillers, the highest around 40 megapascals, and the synergy index of 0.66, more than doubled for the standard baseline. So this confirms the CNT nanofillers effectively exploit the porous anodized surface. So you can see the mechanical interlocking of the CNTs. Okay. So we also tested the flexural performance for our samples. So you can see the micro CT failure analysis. So the results are comparable to the lab shear strength, with anodized samples having higher flexural strengths. You can see the interfacial bond is stable, and we have see the fracture of lower stuffer layers here. Here you can see, and the crack is initiated between the binder layers. So we also did some interlaminar shear strength test just to confirm whether our anodized samples have some advantage over this. So it clearly shows the core phase debonding in sanded aluminum panels, while the modified sanded panels have no sign of debonding on the core and face. So this is my last slide. So we tried to test the fatigue analysis for our samples. So the surface modification and nanofillers delay the stiffness degradation and extended the fatigue life with maximum effect in anodized 0.3% CNT panels. While the multi-walled carbon nanotubes provide highest performance and enhancement, but the GNPs offer lower cost alternatives. So these are slightly behind the multi-walled nanotubes. So both can be used in surface modification and nanofiller reinforcement. So these are some conclusions from this study. So nanofillers amplify the interfacial stability provided by anodized aluminium, establishing the anodized CNT based sandwich panels as optimal interface architecture for fatigue resistant and flexible performance sandwich panels. So the flexible fatigue work is currently ongoing in our lab. So we try to do it at 50, 60 and 80% flexible loads to establish the SN behavior for all these optimized samples. The future scope I will be doing in environmental and long-term durability on these PAA nanofiller interface under moisture and aging conditions. And we'll also try to find out some green nanofillers, alternatives for carbon nanotubes and GNPs for interfacial enforcement. Thank you.
Yeah, your topic and your PhD thesis is very interesting, and therefore I have a question about your graphs. If you return to any graphs, yeah, I will stopping still.
Okay.
Yeah, here. Here is increasing for PAA and CNT 0.3%, and GNP is a little lower. And next graph. Yeah, and there is for flexor strength and flexor stiffness is practically same. Where is or why is this effect?
So basically, if you see the lab shear, so it in the lab shear test, it basically designs to see the interfacial strength specifically. While if you see in flexural test in the bending, so interfacial strength still holds some importance, while the load is being taken by the metal faces and the core. So that's why the flexural response is almost similar for all four
because
sectors.
flexor strength and flexor stiffness is practically similar.
So we'll try to analyze the fatigue. So in fatigue analysis, you can see there is a huge difference between these two loadings.
Yeah.
So we'll in future study we'll try to see the fatigue life for these two structures.
Yeah, and how was condition for fatigue cycle? Which was amplitude? How you have provided fatigue life cycle for testing for these samples? Because you have many cycles, definitely, and you have found it somewhere any stress of fatigue cycle, for standard two parts, and how was provided or created boundary condition of this test?
So we followed like at 10% stiffness degradation. So we tested until the 10% stiffness degradation is achieved for all the samples. So this is the baseline. So in for SN curves we have to test up to the life of complete failure.
How many samples you had it?
So I did 5 samples each.
For each.
Yeah.
Okay. Good. Good. Thanks.
Mentioned that fatigue and cracks develop during the usage and life cycle. So when you are doing the maintenance, service, overhaul, how to check those so that at some unfortunate moment they don't develop into bigger cracks?
Yeah, maybe you can show the next slide. Where is crack? Next.
Okay, this one.
Yeah, here. How will we provide maintenance if will be this crack? Because it can
So one solution is you can use structural monitoring systems, because we are using CNTs and graphenes. So you can use these as you can use CNTs and GNPs in the adhesive, because the major failure is adhesive failure in sandwich panels. So you can sense before reaching its before the failure.
So I mean to say, then should we not have some inbuilt embedded sensors who can sort of
yeah, that's what I am talking about, sir.
Yes.
So the structure health monitoring systems, you can in these systems, what you can do is you can when you are testing your samples, so there is continuous resistance or current flow, you can anything you can measure. So when there is peak or there is a drop,
it's
so
quick with
quick
hammer,
in the
yeah,
sense.
with hammer, and after
Yeah.
how will be
So,
vibration, it must be changed.
based on this data, you can use very models also to analyze these data in your lab, and then these data sets can be used in the software to analyze a minor crack in the
Should I
panels.
say that the aircraft maintenance crew should sort of tinker their testing methods, because at the end of the day it's 60% composite?
Yeah, actually they are using some of the methods.
Please discuss it later.
Okay,
Short of time. Please come for certificate.
Okay, perfect.
Yes. He
Sure. And they are going only with hammer and click, and it will be going. Therefore,
And
it's
please next.
I am also working on the I'm PhD scholar in IIT Delhi. I am also working under the guidance of Professor V.K. Vera, Professor Javed. My working area in my PhD is flame-retardant composite. In my flame-retardant composite, we develop different type of techniques to develop flame-retardant in composite, like coatings, the development of oxy-resins, and doping of the flame-retardant additives in the epoxy resins. So why we are doing the doping? Our main objective is to develop flame-retardant composite for construction panels. Like nowadays Europe and in US, the homes are made by generally by the woods, but the woods are very flame-retardant and very less strength. So here we are trying to replace the wood materials to composite materials, but the composite material also are very flammable. So here we are trying to some approach to increase the flame retardancy, so he can use very easily in the home and the construction industry. So here is my topic. My topic is synergistic flame retardant enhancement in 3D woven glass. I am working on different type of fibers. This is one of my fibers. 3D woven glass fiber for epoxy composite via hybrid nano additive doping. This is my presentation outline. Introduction. As we saw, the modern industrial materials demand very high mechanical strength, lightweight performance, enhanced fire safety due to increased strength building goals. Traditionally, the FR composites offer structural benefits, but often exhibit poor flame retardancy, producing smoke and toxic acid during fire burn. With the growth of higher-rise buildings, modular construction and green infrastructure, there is a critical need for sustainable fire-safe composite system. That's why we have to effort to control fire hazards in polymeric composite material need special testing. Nowadays, as we know, the common materials used in construction industry, traditionally like cement, clay, rocks, etc. What are the issues associated with the conventional sector material? That are being like these are very heavy weight and bulky, lack of sustainability, high energy consumption, carbon footprint, etc. etc. Now, when we look at why we are using composite over the different construction material. We are using construction material because fiber reinforced composite material production similar strength as steel, but they are very lightweight compared to steel. That disadvantage, because of this advantage, lead to the popularity of fiber reinforced composite as an alternative to a traditional steel reinforcement concrete. There are some advantages of fiber reinforced composite construction. They are lightweight, high strength to weight ratio, resistant to rot and corrosion, less repair and maintenance cost, etc. There are different type of composites available, like metal matrix composite, laminated composite, etc. But here in my work, I am working on the fiber reinforced composite. And also in fiber reinforced composite, we are working on 3D woven structural composite, because 3D fabric ensure dimensional stability, conformity, formability. It is also resistant to multi-directional mechanical stress and possessing interlaminate strength and damage tolerance. This is some example of textile used to make building materials, like slabs used to make composite beams and slabs, fiber reinforced composites, tubular 3D fabricated special fabric used to make pillars, and 3D fabricated structural make of walls, the reinforcement of the walls. This is also some example of the composite as shown early morning by my guide, Professor V.K. Now I will come to our objective. Our objective is the development of frame cartridge 3D woven structural composite by hybrid nano coating. In this way, we material taken glass fiber, chisel fiber, epoxy resin, sodium or ammonium phosphate. But here, sodium chemical we mainly use sodium ammonium hydrogen phosphate, nanosilica, nanoplate. This is the properties of fiber. Here I generally use only glass fiber. In discussing only glass fiber. This is our methodology. First we develop manufacture of 3D woven composite, and 3D woven fabric on 3D woven composite with more processing by VRTM method. Then testing of composite. This is a construction parameter of our 3D composite structure. Here we have developed the 3D woven fabric, glass 3D woven fabric, and in the resin preparation, we first use sodium ammonium polyphosphate, sodium ammonium hydrogen phosphate. First we heat sodium phosphate at 120 degrees 4 to 5 hours. After that because it is very hygroscopic, then we convert into fine particles by nano ball milling machine. Doping of nanoparticle resin was done by the two different methods. First one is the mechanical mixing, and further it is done by the sonication method, ultrasonication method. This is the development of composite by VRT method. This is our developed composites. Here we done by three doping parameters: 5%, 5% and 10%. My main objective is to maintaining very much 10% doping is not, because when we add the flame retardant, they will deteriorate the physical and mechanical property. So our objective is try to less use of additive, like 5 to 10% between, so it will less affect the mechanical properties and increase the flame retardancy. So optimize mechanical properties and high mechanical properties and high flame retardant properties. This is the thermal properties of our composites. As you see from the previous cuts, we can observe that the all doped composites show improved thermal stability compared to the neat epoxy glass composites. In the curve, we can see that the main degradation occurs between 320 to 400 degrees centigrade, corresponding to epoxy decomposition. The doped sample exhibit slower mark loss and high residual charge, confirming enhanced condensed phase flame retardant action. Among all formulations, the 7.5% and the 10% dope show higher charge yield, indicating effective phosphate-induced carbonization and nanofiller barrier effect. Further one, this is the flame retardant, main flame retardant test, limited oxidation index and the UL 94. Here we can see that after the doping, the alloy value increased significantly with the increased additive doping. The neat glass composite shows an alloy around 22, but after in 5% doping, the alloy value increased to 26, 7.5% of doping 29, and 10% doping increased 34 alloy value. And here we can see the UL 94 rating. Neat glass also composite had no rating, but 5%, 7.5%, 10% composite show the V2 ratings. Burning stock will be 30 seconds. This is the cone calorimetry analysis. In the core pyramid analysis shows the highest peak heat release indicating rapid fire growth. With nano altitude doping, the peak heat release rate significantly decreases. The 7% doping, 5% doped composites show noticeable reduction in peak compared to the neat sample. Overall, we can say that the 10% and 7.5% doped composites exhibit the lowest peak as error and real, but much smaller peak indicating effective flame suppression. This is the morphology of the char after burned sample. Here we can see that 10% compared to doped composite compared to neat composite show more char formation. It is also the same similar pattern we observe in the 5% doped epoxy composites and 5% doped oxyglass composites. This is the FTI analysis. This FTI factor represents the chemical structure of the residual char after burning. In the doped composite, we can observe that the peaks in the 1000 to 1200 region corresponding to P double bond and SiOS formation. These we confirm the formation of a phosphor silicate reinforced protective char layer. The reduction is CH peaks around 100 doped sample, and in the graph we can see that 10% doped composite gives good char formation and high char formation. This is the conclusion. In our work, successfully developed flame retardant CD1 optical fabric reinforced epoxy. In hybrid system, we use the sodium monomer hydrofurnace so cleared synergistic behavior in improving fire performance. Thermal stability and char will increase significantly compared to neat composite. In the whole work, 10% loading exhibit optimal performance, showing the highest char S2 and improved thermal delay. The future scope, in our future scope, we are also trying to decrease the 10% to 5 to 7% doping and increase the flame retardancy with the help of nanoparticles and optimize mechanical properties. And we also have planning to microcity analysis of in internal char morphology and void distribution, how our nanoparticles distributed in the composites. Thank you.
Possible to make like flammable resistance wall. Let's say we are sitting in the auditorium and maybe fire was catch outside, and at least we feel like that no, we are safe if we are sitting inside this. Actually, that kind of wall is possible.
Yeah, it is possible. It is possible, but at different time. Like it is a BD capacity, like 20 minutes, 30 minutes, 40 minutes, 50 minutes, but not indefinite time. You can only make a different time schedule, like 1 hour, 2 hours. Because
even cement is a like flame resistance.
Yeah.
That's
why I mentioned before. Our work in the like European countries and the US countries where the wood, wooden house is built. Yes. That's why. Because cement is almost they never burn.
Due to furniture only.
Yeah, furniture and the thing.
Accident is going to happen. Huh? Okay, thank you very much.
Thank you. Another question, please. Thank you very much.
Yes.
Good afternoon to all. My name is Prasad. I am from Ulsan University of Technology and Research. In outline of the presentation, introduction, research lab, objectives, material and methods, resultant discussion, conclusion. The natural fiber composites, due to their lower environmental effects such as carbon emission and fossil fuel consumption, biodegradability, lower cost and density, the low density and sustainability, lightweight, also cost effective. So you do natural fiber. Then I use jute fiber because of due to their specific working gravity, low specific gravity as compared to the glass fiber, and higher specific modulus like 40 gram Newton per meter square as compared to the less than that the glass fiber. At least 50% cheaper than the natural fiber, and the flax also, and availability in abundance, and India also highest jute fiber producer of the world. And some advantages of composites made of jute PLA composite: biodegradability, the environmental sustainability, low density and lightweight, good mechanical performance, cost-effective materials, energy efficiency production, good thermal and acoustic insulation, safe handling and health benefit, improved end of options. And what are the challenges associated with the jute fiber making for the composite? It's also moisture absorbency and poor water resistance, poor interfacial bonding, also thermal degradation during process, lower mechanical properties compared to the synthetic composite, and variability in fiber quality, also biodegradability, limited service life, poor flame resistance and recycling challenges. So that we added modified the surface treatment to improve the mechanical strength, biodegradability, and also to strong interfacial adhesion bonding and better strength and stiffness to improve the quality and durability of the composite. And research gap, many researchers have worked in the different types of combination of different like jute epoxy and jute polypropylene, jute polyester, jute polyethylene, etc. But in this study, I used jute PLA. In jute PLA there is a very less work done, and composite made up of different wave achieved of D to D, and I also used the UD fabric. And objectives to study the effect of alkali and alkalic